Today is all about what determinants can do for you. Scaling, invertibility, products, inverses, and the famous Cramer's rule. Think of determinants like a matrix lie detector. When it says 0, the matrix is hiding something. Big picture. Determinants help you decide when a matrix has an inverse and how solving systems behaves. If the determinant is 0, the matrix is basically saying, I'm not reversible. Like spilling coffee on your notes and trying to unspill it. Scaling the whole matrix by k scales the determinant by k to the power n, because you scaled every row. It's like paying the same subscription fee n times. The bill grows fast, and your bank account starts sweating. Determinants do not distribute over addition. Adding matrices and adding determinants are totally different worlds. It's like mixing two playlists and expecting the total mood to be the sum of both moods. You just get chaos. Determinants are linear in one row at a time. You can split a row sum into a sum of determinants. But only one row at a time, not the whole matrix. It's like a diet. One cheat meal is manageable, but cheating every meal is just living. This is one of the nicest miracles in linear algebra. Messy multiplication, clean determinant rule. It's like cooking a complicated recipe and somehow the dishwasher cleans itself too. Elementary matrices are one-row operation machines. Their determinants are simple: k, -1, or 1. Think of them like three magic buttons: scale, swap, or pivot. Determinant non-zero means the matrix is invertible. Determinant 0 means dependencies, like 2 times row 1 minus 3 times row 2 is equal row 3. The proof is basically, if A breaks the space, then AB is broken too. If A is invertible, it is built from elementary moves, and determinants multiply nicely through those moves. It's like saying, if your first domino falls, the whole chain obeys the same physics. This example shows the product rule is not just theory, it actually works. The determinant behaves like a volume multiplier, so doing a then B multiplies the volume twice. Like putting a filter on a filter, the dramatic effect stacks. The inverse undoes what matrix A does, so its determinant must be the reciprocal. If A doubles volume, the inverse halves it. It's like taking a bad selfie and using undo. Except math actually lets you undo perfectly. Wrong row cofactor dot products give 0 because it secretly becomes the determinant of a matrix with two identical rows. In other words, the determinant catches you cheating. It's like trying to use someone else's password. The system says, "Nice try," and gives you 0. Adjoint is just the transpose of the cofactor matrix. So the hard work is cofactors, and the rest is flipping the table. Literally. It's like finishing a long essay and then the last step is just printing it in landscape. This is a clean example. Once the cofactor matrix is known, the adjoint is just transpose. It's like building IKEA furniture. The hard part is the first 20 steps, and then step 21 is turn it upright. The punchline is that if you multiply matrix A by the adjoint of A, it becomes determinant times the identity. Then dividing by the determinant gives the inverse. It's like paying off a debt and suddenly your balance becomes exactly zero everywhere. Beautiful and suspiciously satisfying. This method is powerful but can be expensive. Cofactors can be a lot of work. Still, it's a real formula that always works when determinant is not zero. It's like having a spare key, but the key is made of paperwork. Cramer's rule says each variable is a fraction of two determinants. It's elegant, but not always practical for big systems. Think of it like solving a problem with a fancy sword. Impressive, but you don't bring it to every fight. The proof is basically, write x equals A inverse times b, replace the inverse with adjoint over determinant, and then notice the numerators are exactly determinants of the modified matrices. It's like discovering your complicated expression was secretly a shortcut the whole time. Cramer's rule gives the solution directly using determinant ratios. It works perfectly here because det A is not zero. If det A were zero, Cramer's rule would be like dividing by zero, the math equivalent of trying to open a door by politely asking the wall. This theorem is like a Swiss Army knife. Any one condition unlocks all the others. So if you can show det A is not zero, you get invertibility, uniqueness, and consistency for free. It's like showing your student ID and suddenly getting access to the whole campus. Determinants are the shortcut to big truths, invertible or not, unique solution or not, and how volumes scale. If det A is zero, something collapsed and you cannot reverse it. Like trying to unmix your coffee after stirring. The universe says no, even if you believe in miracles.